afternoon, everybody. First of all, I would really like to thank the Academy for this wonderful opportunity in front of this wonderful audience. This is a huge shift from what we were just hearing. So, but I promise that at least the first few minutes will be very familiar to almost all of you. So, right. So I begin with something very, very simple. We all have seen that orthogonality in Rn, dot product we understand in Rn. In Cn, we take conjugate linear in the first coordinate, linear in the second. Then with these dot products, there is a length of vector, which is this. In Rn, it's mod x1 square plus mod x2 square plus mod xn square to the power half. And orthogonality is just inner product of xy equal to 0. So these are two orthogonal vectors. We all have seen that. You can tilt them a little bit if you like, but this is the beginning point of our study. Okay. So this is a simple situation for us, and quickly, because I will soon go into my matrices, but I'll come back to vectors just in the next slide. If you have the space of n cross n complex matrices, then you can still define an inner product. As soon as you have an inner product, which is the dot product, using the trace of matrices, again with the same procedure like we just did, there is a norm, that is the length of a matrix, which is derived from this inner product, this dot product, and there is a simpler way to look at it. So if A was this matrix Aij, entries A11, A12, A1n and so on, then this norm will precisely look like summation of the mod square of all the entries. So that's something that we all understand, and then we can define orthogonality with respect to this inner product, which is just trace of A star B equal to 0. So that's our simple situation. Okay. Okay. So one term in my title was orthogonality. This is the simplest orthogonality that we understand. Next term was some approximations. So here is some motivation why we study approximations. There are lots of other motivations, but this is just one. Given in a usual vector space course, linear algebra course, we understand that whenever we get linearly independent vectors, Gram-Schmidt tells us how to orthogonalize them. Okay, I see a lot of nodding heads from the students, so that's good. Right. The problem is how to find the one which is closest to your beginning vectors. Okay. And in chemistry itself, in some models, quantities are expressed as orthonormal vectors. Okay. But then experimental observations give us which are not orthonormal. So I want to find something that is closest to my observation, right? And this was done by Loudon through his orthogonalization process. If you have heard about it, good. If not, then here is a very nice article by my supervisor, Professor Bhatia, in Resonance, where he explains all this and its connection. But let's skip to our general thing. Okay, so quick thing, answer to that question. Gram-Schmidt wants us, gives us an orthonormal basis out of linearly independent vectors. Question was to ask which one is the closest. Matrices are close to our heart, so Gram-Schmidt can actually be written as this particular formulation in terms of matrices. So now my initial vectors A1, A2, An, I look as the columns of A. So if they are linearly independent, my matrix is invertible. And then Gram-Schmidt, what it actually does is it gives you a unitary matrix Q, which is basically your orthonormal basis, and an R, which was the remaining what you get in the process of orthonormalization. And if you impose this condition that R should be an upper triangular matrix with positive diagonal entries, then this is unique. This particular factorization is unique. Another interesting decomposition of an invertible matrix is with respect to the polar decomposition. So there are some terms. U is again unitary, orthonormal columns. P is a positive definite matrix. Okay, and out of all these unitaries, actually this is the unitary which is the closest to A. So that has been already shown in literature, and this is the one that Loudon actually found. Okay? It boils down to this in matrix theory. So that's the beginning of motivation for why to study approximations in matrices. Okay? Now this is a very, very simple norm for us. So I'm going towards more mathematics now. So if any matrix A can be decomposed as singular value decomposition. So there you get two unitaries and a positive diagonal, non-negative diagonal. And then this was my, with respect to these are known as singular values of A. And then this Frobenius norm is nothing but the Euclidean norm of the singular values. But then there are more interesting norms on matrices. The supremum norm, the spectral norm, operator norm, then the Shatton P norms, numerical radius, Key-Fahnke norms, and so on and so forth. So the idea does not stop at inner product for us, and that's the bottom line of everything. So here is one more quick thing. In general, the problem is this, that if you have a subspace, there is a vector outside, you want to find the closest vector W here, which is the closest in this setting. So in our RNCN case, we have this inner product, everything is very nice, and the orthogonal projection got by that is precisely the one that is the closest. But this norm, I don't want to stick to this norm, but this norm was coming from an inner product. Orthogonality was defined via an inner product. I want to escape that and go to more general settings. So this is the best approximation that I just said. Okay, so now I want to go to more general settings. There are more norms on vectors, more norms on matrices, which are more practical, which come from various applications here and there in quantum mechanics, everywhere. So I cannot just stick to this Hilbert-Schmidt norm, which was coming from the inner product. So when I ask the question of best approximation, one question is, when is 0 the best approximation to x in my previous setting? That means I have this relation. When there is an inner product and the norm was coming from an inner product, then this is precisely when you have orthogonality. So now this becomes my new definition of orthogonality, escaping the inner product, but just with the help of the length of the vectors. So norm is the length of these vectors. Okay. So when I change norms, this still makes sense. Inner product is gone. Okay. More generally, if I want to stay in vector subspaces, then I would ask this question. Right. So this, again I repeat, when is 0 the best approximation to W from X? Okay. So I will say that X is, in the next slide, I will say that X is said to be Birkhoff James orthogonal to this subspace if this condition holds. Okay. And this was initially done by Birkhoff and James, therefore the name Birkhoff James. Birkhoff initially did it only for R3, but James really truly generalized it in norm-linear spaces. Okay. Okay, so here is my situation in Mn. I'm back in Mn. Remember that I had an inner product, but this is the operator norm now. So for two matrices, Bhatia and Shemrel in 1999 had this remarkable result, which has these days a lot of studies going on with just this result in the past decade. So they said that A is orthogonal to B in the Birkhoff James sense. Now in this norm, if you can find an underlying unit vector where A attains its norm and Ax Bx are orthogonal in the usual sense. So now Ax Bx are vectors in Cn. Okay. So it connects a more complicated Birkhoff James orthogonality to the standard orthogonality in Cn. Right. So here is where they did it. Okay. So what we did initially was, with Tirtho, who is sitting here, we developed a new method of looking at this particular problem via different lens. So this was a very simple idea. So remember that if x and y were vectors, then this is, and suppose I was in real space, which is easier to understand, then my t would be coming from reals. Now if I look at this function which takes t to norm x plus ty, then saying that x is orthogonal to y would be the same as saying that f is attaining its minimum at 0. But then this is attaining minimum at 0 is a calculus problem. The only problem is my f is not differentiable because norms are not differentiable. But then these tools of convex analysis come into picture because norm is a convex function. And that's where the idea of subdifferential comes in. So here is the idea of subdifferential. Here is a picture which will make it more clear. Definition you can read later. Okay, so if everything was differentiable, for example, at this point I have one single tangent. Now this is a convex function, and suppose at this point there is no differentiability, then I would have multiple tangents. What I am really doing is collecting them and forming a set which is known as the subdifferential set. Okay. Now this idea really helped us because when I say that f needs to attain its minimum value at a point, it just means to say that 0 should be in the subdifferential set of f at that particular point. And many mathematicians have studied this subdifferential set for various norms, and we did it further for our own cases whenever we needed it. So that was the main idea that we developed and are still using it because it helps us getting various very strong results in several settings still. So, okay, sorry. Okay. The main objective was that earlier only orthogonality was known from, for example, A is orthogonal to B was known. But what if I want to say that A is orthogonal to the whole subspace of Mn? Okay, so this problem has been studied for quite some time in general. I mean, approximation problem, finding the closest, for example, in trace 0, the subspace of trace 0 matrices, we know that this is the closest. In the space of real subspace of Hermitian matrices, we know that the real part of A, which is the Hermitian part of A, is the closest. But then the more general problem was actually solvable by this idea of subdifferentiability. So we could actually use that idea and say something very strong in terms of orthogonality as well as approximations and several more. So this was again an old result. So we said that if for any subspace you can find a similar characterization, but this time you will not get a single vector, you will get a density matrix, okay, which does similar things. So A star AP is norm A square P and AP is in W per, and then there are more conditions on P. Okay. One of the implications was that this result of odd and earth had a very simple proof using our previous result, which I am not presenting here, but here is the what this result actually does is that it relates the distance of a matrix from this particular subspace to the maximum of quantum variances. These are quantum variances of A. Okay. Okay. So Bhatia-Shemirel theorem again looks like a simpler version of our result in terms of density matrices, which is just presented here to have a look that something is similar. Okay. These are also related to another area which is now coming up as minimal matrices. What they do is that they actually allow us the description of minimal length curves in this flag manifold. Okay. So the existence of minimal matrices allows some description of these minimal length curves in this particular manifold. But minimal matrices are nothing but really our relation of orthogonality in a very special case. So here A should be Hermitian matrix and D is nothing but the subspace of diagonal matrices. So whenever this relation is true, so from that area also this is coming in, that A is said to be minimal if this condition is satisfied. But in our notation it's nothing but saying that A is orthogonal to the subspace of diagonal matrices. So again this was a result that was done for minimal matrices, but then it again looks like a particular case of our result. So that strengthened it. More general settings for people who can understand. So again quantum mechanics wanted to look at algebras of physical observables, and those structures brought up C-star algebras. So we want to extend our whatever we have known to these settings, and this we did in 2021. So if A is a unital C-star algebra over any field with identity, and assume that C star subalgebras of A also contain identity. Then similar notations are there. B is a subspace. Okay. Distance is this. Then if you have this set of states, I'll just take 1 minute. Slides are almost over. Then you can have a similar thing, that if you can have a best approximation characterization in terms of the states. And in the next slide, you will see that it is something extremely similar to what we have just seen in matrices. Matrices are a specific finite dimensional C star algebra. Block diagonals are subalgebras, C star subalgebras. So what we just said in the terms of Birkhoff James orthogonality is that if you take a subspace of a C star algebra, an element of a C star algebra outside the subspace, then it's orthogonal if and only if there is a phi from the state. Again, at A star A it attains norm, and at A star B it's 0. And there is a semi-inner product with respect to every such phi, which is precisely given by phi A star B. So it's exactly the same as we were doing in matrices, but only difference is this time it's coming from this phi. So again, this was done recently. Yeah, that's where I will end. Some more work in this direction has been done in these recent papers, which I have not talked about much, but this is the survey article that if you're interested in, you can have a look. It has almost everything related to that. Okay, thank you.
Thank you so much. Any questions?
So does your theorem apply there?
Yes, it will.
I see.
It will.
For symmetric as well as antisymmetric.
Yes, because it's for a general subspace. Our theorem is for a general subspace. More conditions can be imposed on that density matrix given the structure, but it will work. Yes.
Thank you.
Thank you.
Thank you.